Okay, so we'll begin the abstract definition using the regroupoid. So this is actually in the book, the Cambridge University Press, this Adam's book. So I will give you reference. So this was in the first lecture. So the book by Adam. So we'll try to avoid using definition using category theory. So it's related to some theory of stacks in algebraic geometry. So as much as possible and use more concrete set theoretical approach here. So these are really sort of a quick version of a more general construction. So here a topological groupoid. So this is not the groupoid that we talked about in the first lectures here. So it's just some other objects. Uh, so they use all kinds of terminology very similarly, but so a topological groupoid consists of a space C0 of object and the space of arrows with five continuous maps. So space C0, you can think of it as a manifold usually. And G1 is sort of a manifold of arrows. Okay, so they have usually some topology, and both have topology. So what they have is a source map. So S goes to G1, and the target map G1 goes to G0. So it means this arrow has a beginning and the end. Okay, so this source map has to be defined, and the associative composition map M. So 1S times T1 um, goes to G1S goes to G1 goes to G1. Okay, and the unit map U goes from G0 to G1. Okay, so you can think of unit map as some arrow that goes from itself to itself. Okay, sort of identity map, and which satisfy S UX as X, and then T UY. Right. So this means that this arrow, if the arrow ends at some point, then by the so this S times T means that this right, if this arrow here ends at some ta at the target, then the source of the second map has to be the same as a target, and then you can compose this to get a arrow at G1. Okay, so something starts from here and then ends at at G, and then that has to be source in Y. So you only multiply those. Okay, so that's what it means. And the unit is that the G0 goes to G1, so that the source is X, and then so this should be X again. So TUX, so the terminal is X, and then if you multiply GUX, then this is again, so you're composing trivial one with a G, so it's just the same as G, and then the same as UXG. Okay. So of course, when you want to multiply, then this means that so the source of G has to be X here, and then here the terminal point of G has to be X here. Okay. So I mean, this arrow has to compose. So this is a categorical thing. So you have so always whenever you multiply, you have to have a target has to be the target of the first map has to be the source of the second map. So these are the morphisms in the category theory. And then, of course, there's an inverse map, so if G is an arrow going from X to Y, so these are morphisms. So you can think of X as an object in category, and then G as the morphisms. Then IZ is going from Y to X, and IZG is UX. So you go to G, and then you do the inverse, then that's the unit. Okay. So topological groupoid has to have this I map as well, inverse map, and then the GI IZ is UY. Okay. So G has a source is X, and then terminal point is Y. Then so then this means that when you go from X to Y on the G and then IZ, then you have to go back to X. So it has to be the unit one. And then here, if you go from Y by IG, and then you go back to Y by G, then you have to go to the UI. Okay, so there's this five continuous maps. Okay, and of course, so by continuous, I mean that this G1 also has a topology, and it's continuous with respect to this topology here. And so it's a sort of a category, but it has a uh, topology on the space of arrows and the space of objects. Okay, so that's the difference. So it's just not a category. Okay, so of course, it's a type of category with more restrictions. Okay, so so you can think of these errors as morphisms. So the collection of morphisms has some topology. That's the point here. So D group point is one where G0 and G1 is the smooth manifolds. Okay, and so M is a smooth manifold, and you can let G0, G1 to be M, and then all the maps to be identity. Then this is again a groupoid called just a unique groupoid. Okay. Um, all the morphism in G1 to be identity. And of course, you can trivially construct these source map and target map and unit map. So those are trivial. Okay. So isotropy group at X is a set of all arrows from X to X. Okay, so it just goes from X to X. So you collect those points. And the homomorphism of a D group with V goes H to X. G is a pair of smooth maps, V0 going, so H has a H0 and H1, so you get this smooth maps H0 to G0, and then H1, V1 goes to H1 to G1, and which commits with all the structural maps. So that will be called the groupoid homomorphism. And fiber product, so I don't think we need it, but probably need it in some proof, part of the proof. So we have a two homomorphism from H to G and K to G. So G is the same regroupoid, and then you can form a fiber product. So this is a regroupoid whose objects are the Y, G, G for Y in H0 and G in K0, and G arrow going from phi Y to psi Y, psi Z, and so and then these will form some manifold, and then uh, the arrows are, so these are the objects. So the arrows will be the pair of HK of arrows, H to Y prime, and then K to Z prime, so that there's a commutativity condition here. So it's more like the fiber product in covering space theory as well. So what they are actually wanting to do is like the covering space theory. So or at least in the so if you have two topological space maps like this, then you can always form a fiber product using this kind of idea, which is that you take any inverse images, and then um, you look at the subspace which goes to preserves this kind of property under for the induced maps. So like if you think of this as bundles or some maps, then so you can kind of it's generalizing that kind of construction here. So it's so phi is a say Lie homomorphism. Then it's a Attal map. Attal map means that it's a local homeomorphism between uh, the G0 and the H0. I mean the G1 and the target G1, and then the zero-dimensional objects, and then to the dimensional map. So it just means a local homeomorphism. And it induces isomorphism of stabilizer group from X to phi0X. And then also it induces bisection of the orbit spaces. So if G and G prime are differentiable Attal groupoid, then the phi going from G to G prime is a differentiable equivalence if P0 is equivalence and is a local diffeomorphism. Okay, so we need the diffeomorphism condition if you want a differentiable case. Okay, and the ethyl here just means that these source and target maps are local homeomorphisms. Okay, so ethyl means this. Ethyl just means that these local diffeomorphisms, local homeomorphisms. That's what. So these are again in the book of Adam here, Adam. So this will generate an equivalence relation on group Y. So you have an equivalence, and then so this is just not an equivalence relation yet. So whenever you have some binary relation, to make an equivalence relation, you have to extend it. So you have to include all the going back and forth, and then compose all that to make an equivalence relation. So this generates equivalence relation, but the point is only the Morita equivalence is enough. So that means Morita means that there's another object which is equivalent to. So if two are equivalent, then there is a third object which is equivalent to this, and then equivalent to this. Okay, so that's the Morita equivalence. Okay, so that will be enough to understand all the equivalence. Is just you need just one intermediary. Okay, so ordinary equivalence relation you have to go through many type of going back and forth, but Morita means that there's just one intermediate object. Okay, so those are the Lie group points, and so nerve of the group point. So you have any Lie group point, then you can define Gn where these GI is a sequence where the source of GI is the target of the GI plus one. So you can just go from one to the next. So you can take a product. So you can think of it as a fiber product, and the phase operator is Di goes to Gn minus one, sending this to this, and then which is just you compose the ith one with Gi plus one. So this is so if you look at all these objects, and then you find these face maps for each object. Okay, so Gn to another Gn. So then this is some sort of a simplicial manifold type of situation. So of course this is an infinite dimensional object because you can do many of these compositions. Uh, So the classifying space BG is a geometric realization of this simplicial complex. Okay, so that's and orbifold X with the G as a Lie group, for it has pi n defined as the pi n of this BG. So orbifold will be realized as a Lie groupoid. Okay, so then you can compute the fundamental, I mean the high homotopy group like this. Okay, so now we define our orbifold as a Lie groupoid. Okay, so let Lie group K acts smoothly on M, then the action of the Lie groupoid L is given by L0 being M, and then L1 is K times M with S projection, and T is the action. So we have some M, and then Lie group acting on it. Then you can define a Lie groupoid by setting L0 to be M, and then L1 to be this manifold, K times M, with source being the projection and T being the action. Okay. And of course, I have to define other things, but so I'm not defining these yet here. Okay. And an orbifold groupoid is a proper ethyl groupoid. Okay, so proper means that all the source and target maps are proper maps, and then ethyl means they are local homeomorphisms. Okay, and all the other maps are local homeomorphisms and so on. And of course, it's a Lie groupoid. Okay, so that's the orbifold groupoid is. And the proper means that the S times T going from G1 to G0 is a proper map. Okay. And the group void is Atari, P and T are local diffeomorphisms. And so then, so let G be a proper effective Atari group void. Then its orbit space can be given a structure of an effective orbifold. Okay, so effective means that effective orbifold means that the group acts faithfully. So I mean the local group acts faithfully, and and of course here proper uh, at effective in the groupoid entire groupoid means that so then then this is going to be give you the orbital structure. So you look at orbit space. So orbit space means that all the points equivalent to on the point by this arrow. So you have these arrows, and then you compose all that. And then this means that this composition will be any image of these under these or these arrows will be considered the orbit. So you look at all the space of those, and then you take the quotient space. Then that's the orbit space. Uh, so then this can be given the effective orbital structure. So proper effective entire groupoid is an effective orbifold in some sense. And then of course the converse can be also obtained, right? So as an example, so if you have a smooth manifold with atlas U and then M0 be just disjoint union of these all these open sets. So we just consider them as a disjoint sets, and then M1 be the U times XV. So you look at the all the product of U times V with X. So this means maybe I should say M there, but so the whenever you identify the 2 points identified in M, then you can when they identify you can introduce arrow there. So that's the space. So this is some subset of the U times V which gets identified on M. Okay, so you look at all these sets, and then this will be a manifold, and then the space of orbits is M, and then of course the orbifold. So then this will give you a proper effective entire groupoid, okay, whose orbit is M, okay, and the orbifold structure is of course given by this U. So again, if you have an orbifold, you can do the same sort of construction. So you cover it by orbifold atlas, and then you look at all this disjoint union U tilde in this case, and then M1 is U tilde times V tilde, and then the points which are identified by the group actions will be the subset which you want to look at, and then the space of orbit is the G bar, and then so from the orbifold you can also go back to proper effective hetero groupoid. So you can go back and forth. So I guess this is a convenient way to characterize orbifold in terms of a groupoid, but I guess that this is not but because then you can use lots of tools in the groupoid, like computing for the fundamental group and so on, and the higher homotopy group and so on. But of course, these are, I mean, groupoids are much more versatile object than the orbifolds. So let's think about, yeah, so this is our space. So let G be, so we talk about the action of the groupoid. So let G be an orbifold groupoid. Left G space is a manifold E equipped with an action by G. So such an action is given by 2map, which is an anchor, which goes from E0 goes to G0, and then and the action G1 times C0 goes from E to E0. So whenever you have some orbifold group, or you can you can define you can talk about the left G space which is that the map like this. So so times t0 means that the so the source has to be pi e, and then and then it will go to the terminal point on the G1. Okay, so that's how it acts. And the map is defined by GE with pi e going to the source, and then so mu e g is the g times e. So you take some uh, right. So you have point E in here, and then you take pi goes to the source of G, and then the product is the so mu is the product is the end which where the G send E to. Okay. So so then it satisfies action property that the pi GE is TG. So so you send the source to the terminal point here, and identity X is E goes to E, and G. Uh, so for any X, the trivial arrow is send E to E, any point to E, and GH is GHE for H X Y, and then G Y G, and E is in with pi E is of course X. All right. So for this tool, you have to have this condition. And of course, right G space is a left G off space obtained by the switching the target and the source map. Okay, so you can do that. So this is again useful for some things later.